All right, the 2018 BC question number 2 on the free response was a question that every student absolutely hated. And so if you hated it too, feel like you've got a community there. So we've got, again, we've got plankton cells. We don't really care about the plankton. They tell us at a depth of H meters, the density in millions of cells per cubic meter, I'm going to rely on those units in a little bit, is modeled by P of H, where again, H is in meters, and that's valid when H is between 0 and 30, so from the surface of the sea to 30 meters deep. And then there's a separate model for the density of these plankton when H is greater than or equal to 30. So it starts out fairly simple. It wants P prime of 25 and P prime of 25. I'm going to just do on my calculator. Okay, so I'm literally just using the Math 8 feature. And if I plug in, I'm going to get of 1.179. Please be careful that you keep all your 3 decimal places. Otherwise, you're not going to get credit for your answer. As far as using correct units, I just took the derivative of this it was already in millions of cells per cubic meter. So this is going to be in millions of cells, and it was per cubic meter. But because I'm taking the derivative with respect to H, which is right, because it's P of H, I'm taking the derivative with respect to H. H is 25 in this moment. So it's going to be per meter to the 4th power now. Okay. And it's when H is 25, or I could say when we're 25 meters below sea level, or 25 meters deep. Okay. The meaning of this is that it's a derivative, so it's the rate of change of whatever I took the derivative of, which is the density of the plankton cells. Okay, so it's the rate of change of the density of the plankton cells. I've already used my units up top here, okay, when H equals 25. Okay, so again, it feels super awkward because we're like, we don't understand what the density of plankton means. We don't like the units on this, but I took a derivative. It's a rate of change. What is it the rate of change of? P of H. What is P of H? It's the density of plankton cells. So you don't have to rewrite the wheel. That made no sense, but you guys get what I'm trying to say. You just have to rely on what we know. All right, part B says to consider a vertical column of water in the sea with horizontal cross sections of constant area 3 square meters. To the nearest million, how many plankton cells are in this column of water between H equals 0 and H equals 30 meters? All right, so the fact that P of H is in millions of cells per cubic meter, that's already, anytime you have pers involved, that is a rate of change. So what we're going to need is we're going to need to integrate to get back to our just millions of cells, which is because I want to know how many plankton cells, right? So that should indicate to you guys, because I'm going from this rate, it's a rate of change sort of unit, that I'm going to have to integrate. And so let's see, I'm going to integrate from 0 to 30 because it says from 0 meters to 30 meters. If I just integrate P of H with a DH at the end, this is in millions of plankton, millions, oh my Lord, it won't let me do polka dots, millions of plankton per cubic meter. And then the H here is in meters. So far I have millions of plankton per meter squared, which is where this 3 square meters comes in. So now if I multiply this by a 3, what I then have is meters squared there. And so when I multiply these out, I end up with just millions of plankton. Okay, so again, I didn't really understand what the heck they were asking me. I just relied strictly on units. I relied on the fact that in order to go from a per unit, millions of cells per cubic meter, I needed an integral. And then inside my integral, I made sure that my units would work out so that I was left with what I wanted, which is just millions of plankton. And I'm going to integrate this on the calculator, and I will get 1,675.415, and it asks for the nearest million. So we're going to say that this is approximately 1,675 million plankton. Okay. All right. So far, no fun, but let's keep working at it. See, we had to read this like 5 times to figure out what the heck is going on here. Okay, so I'm taking the same column from part B with a cross section of constant area 3 square meters, and I want to know the amount of plankton in the entire column. So the thing about this is that I'm going to use the integral from which gave us the amount of plankton in the original up to the depth of 30 meters. I'm sorry, guys. So the amount of plankton from 0 to 30 is the integral from part B of 3 times P of H dH. And just as a little reminder, this was in square meters. This is in millions of plankton per cubic meter. And then my H at the end was in meters, and that's how I ended up with just millions of planktons. Okay, and then I'm going to have to add on the integral from 30 to K, because it's saying that we're K meters deep. Okay, and once I hit 30, I'm no longer using the equation P of H. I'm now using the model F of H. Okay, and we're assuming that the units on F of H are the same as the units on P of H. So I'm going to need, it's the same thing. This is going to be in millions of plankton per cubic meter. Okay, and then we're going to multiply by the 3, which is the cross section in square meters. And then I'm going to multiply by D of H, which is in meters, and that's how I'm going to get millions of plankton. So this is going to give me, these 2 integrals combined are going to give me all of the plankton cells in millions in the entire column. Okay, so I have these stupid looking integrals, but now I have to explain why the number of plankton cells in the column is less than or equal to 200 million. All right, so I labeled this part B, but it's really part C. Take a second to note that so far, I know this is like the most uncomfortable problem, we've got half of part C done already, okay? Or maybe more than half, maybe 2/3 of part C done already. And now I just have to explain why the number of plankton cells in the column is less than or equal to 200 million. Well, we said that in part A that this was approximately 1,675 million. Okay, and then they give you this stupid stuff about F of H being less than U of H for H greater than 30, and they gave us this. Okay, so I'm going to take this integral from 30 to K of F of H dH, or I'm sorry, times 3, and I'm going to say that this has to be less than or equal to, because it's less than or equal to, the integral from 30 to K of U of H times 3 dH. All right, because F of H is less than or equal to U of H according to what they said here. All right, so that means that the integral from 30 to K of 3 times F of H dH has to be less than or equal to 3 times the integral from 30 to K of U of H dH. And I know that the integral from 30 to k has to be less than the integral from 30 to infinity. Sorry, 3 times the integral from 30 to infinity of u of h dh, which is going to be less than or equal to 3 times 105. Okay, and that gives me a 415. Sorry, this is why I tell you not to simplify. That gives me a 315. Okay, and so therefore, the two integrals added, the integral from 0 to 3, 30 of 3 times p of h dh, plus the integral from 0 to 30 of 3, I'm sorry, it's not from 0 to 30, it's from 30 to k, of 3 times f of h dh has to be less than or equal to 1675 plus 315, which is less than 2,000 million. Okay, there was a lot here. It was not easy. It was very annoying. It kind of messed with your head a little bit. And then, unfortunately, we're not quite yet done. All right, but I just did, again, 2/3 of your points are going to come from setting this up. This is probably 2 out of 3 points for this part. And the last point is going to be all of this crap. So if you didn't get to the very end of it, don't stress about it. All right, let's look at part D. D completely just leaves the whole concept of all the plankton and everything like that. You've got a boat on the surface. We want total distance traveled. We're given our function in terms of we're given our rates of change as a vector where we have x prime of t and y prime of t. So my total distance traveled is going to be the integral. It's the arc length formula from parametrics. So it's going to be the integral from 0 to 1 of the square root of x prime of t squared plus y prime of t squared. And you just needed to know this formula. Okay, and then once you have that, you enter it into your calculator and you are done. So if we integrate this, we get 757.455 or 757.456. Those are the only two acceptable answers. It doesn't ask me for units. It doesn't ask me for an explanation. It doesn't ask me for a justification. I've shown my work to the best of my ability on a calculator question. Okay, so part D was a total jump off from all the confusion from parts A, B, and C. Even if you got super hung up on part B or part C, you can still get to part D. So just because the early parts of the question are hard doesn't mean that all parts of the question are going to be hard. They don't get consecutively harder. D was a jump off to almost like a completely different topic. Not almost, it was a completely different topic. It was suddenly parametrics, but it was something that was very attainable. So just mind yourself when you're transitioning between things.